Hello everyone, this is Sri Manika Makam, and in this video I'll discuss everything that I've done in ENPM 8090 course at University of Maryland. This course gave me an opportunity to work with robot hardware and software simultaneously, and it was pretty exciting. First, let's look into the robot's hardware. The base of the robot is Baron 4WD mobile platform. You can see that the wheel and the motors have been fixed. The first component is the wheel encoders. So they have been fixed to the front left and the back right wheels. So the wheel encoders are basically used for position feedback. Like with the help of the number of counter ticks, we can estimate how far the robot has moved. The next component is the Raspberry Pi 3 Model B Plus. This is like the brain of the robot. All the code that has been written in Raspberry Pi is in Python, and this acts like the logic for the autonomous driving of the robot. Next is Raspberry Pi Camera V2.1. This is like the eye of the robot, where where the robot can see how the environment looks like, and it's used for functionalities like object detection, QR code detection, arrow detection. The next is hedge bridge. This is used to control the DC motors. Like with help of this, we can make the motors run clockwise or anti-clockwise. The next is ultrasonic sensor. The model uses HCSR04. It's a distance sensor where we can estimate like if there's any obstacle in front of the robot, and can be used for obstacle avoidance. Uh, the next components are the power sources. I've used a power bank for powering up the Raspberry Pi, and I've used five batteries for driving the motors. So to have an pick and place functionality, we want to have a gripper for the robot, and here I'm building the gripper using a servo motor. So this will help in picking up the object and placing the object wherever we want. The next component we are fixing is the IMU. The model used here is BNO055. IMU is really important for orientation feedback. So with the help of wheel encoders, we can't be sure that the robot will move in a straight line. But with IMU, we can always like rectify its orientation and make the robot move in a straight line. It's also used for like perfect turnings. Like if you want to move it to 90 degrees with the help of IMU, we can do that. Uh, this is being hooked up to a Nano, and Nano will later be hooked up to the Raspberry Pi. So the main purpose of this course is to complete our grand challenge at the end of the semester. To achieve that, we've completed like four different modules. That is perception, locomotion and kinematics, localization, planning and navigation. Now we'll see the tasks we performed in all of these modules to get ready for the grand challenge. First is the perception module. Here we'll see the functionalities by Raspberry Pi camera and ultrasonic sensor. In this demonstration, we show the detection of green traffic light and also its tracking. To achieve this, we first take the HSV mask of that green color. Uh, then after segregating out the green color, we find the contours, and from the contour, we find the radius and center of it to draw the circle around it. This same procedure will be followed to detect an object in the grand challenge. In this demonstration, we'll detect the arrow mark and also predict its direction. But I face some problems in taking out the HSV values for an object or an arrow mark. That's because the HSV values change from one lighting condition to another lighting condition. To overcome this problem, I had to make sure that there are static lighting conditions in my arena, and this helped me figure out to get the proper HSV values. Here is a demonstration of the detection of the QR code. QR codes can also be used for localization purposes, just like arrow, and it will be used in the grand challenge. This image describes the functionality of the distance sensor. Here we can see that it detected the bunny at a distance of 43.23 centimeters. So this can be used for obstacle avoidance. Next module is locomotion and kinematics. Here we'll see the functionality of gripper and also the teleoperation of the robot. This is the demonstration of the complete duty cycle of the servo motor. First, I achieved the teleoperation of the robot by testing the forward, reverse, and right and left operations. Then I combined the pick and place functionality with the teleoperation of the robot, and here is the time-lapse video of the same. Next module is localization. Here we'll be using wheel encoders for position feedback and IMU sensor for orientation feedback. Here is the experiment to run the robot for 1 meter distance in a straight line. To achieve this, we need feedback from both the wheel encoders and the IMU sensor and implement a PID. So, I wasn't able to run the robot for 1 meter exactly when I'm trying to access the IMU readings because the counter ticks and the IMU readings are not published at the same rate. So what I had to do was create another thread where my counter ticks will be calculated. And in the main program, I just had to access this counter ticks whenever necessary and use my IMU readings as it is to rectify its orientation. And whenever the counter ticks reach to a specific limit, I stop the robot. That is, we achieve the exact distance that the robot has to move. So, with the help of this multi-threading and the sensor feedback from IMU and the wheel encoders, I could make the robot move in a straight line for a specific distance. And for turns, I've just used the IMU readings because only the orientation matters, and there I didn't use any wheel encoder feedback. The next module is planning and navigation. Here we achieve the autonomous tracking and retrieving of the objects. In this experiment, we can see that the robot tracks the red object and aligns it to it so that it can go and pick it up. Now, let's talk about the grand challenge. So, the arena is 12 feet by 12 feet, and there's a cold storage area which is 2 feet by 2 feet, and the injection area is 2 feet by 2 feet with a clustered environment in the middle. So, there will be three vaccine vials in cold storage area, that is one Pfizer, one Moderna, and one Johnson and Johnson. The task is that the robot should be autonomously be able to track a vial and uh, uh, take it to the injection area and drop it there. So this has to be done 3 times. That is, the robot should be able to pick one vial at a time. The run starts when professor sends an email, and after that we have to show a QR code to the robot with which it decides which vial to pick up. So depending on the first QR code, it picked up the Pfizer vial, which is red block, and it's moving towards the injection area. And now it sees the purple arrow mark and aligns itself towards it. Now it reaches the injection area, and by showing up on the face, it drops the vial and moves back. Now it detected the green arrow mark and aligned itself towards it, and now it's going back to the cold storage area. Now the robot has been shown the second QR code. Here it was supposed to align itself towards a QR code which is above the vials, but it couldn't, so it can't see the vials and it couldn't pick up any. So it will continue with the course without the vial. It again saw the purple arrow mark and it's moving towards. So now in the middle, professor said that stand in front of the robot and the robot stopped. So it has the obstacle avoidance functionality. In the previous frame, we could see the robot's trajectory on the right side. There were definitely a few problems that I faced. The movement on the carpet was very problematic, and there was a lot of slip on the carpet. The turnings were very difficult, as you can see in the video. Like it took a lot of time to make a turn, and that's where I lost my time, and I couldn't make a course for the third while. But overall, I'm really happy with the course, and it was great working with the professor. Thank you all for watching.